Alright, in this video we'll be talking about the series and parallel combination of resistors. Now in series, this is really easy. All you have to do is add them together. So Req, the equivalent resistance, is just the resistors linearly added. Like so. So for example, if we've got a circuit with 3 resistors, some voltage in, and we've got some current going through it. The current across these are all going to be equal, and we can find the equivalent resistance using Kirchoff's voltage law, because we know that the voltages here have to sum to 0. So if we say V1, we've got here across the first resistor, V2 across the second, and V3 across the third. We can write a system of equations like so. Starting at the source, we know VO is going to be equal to V1 plus V2 plus V3. Using Ohm's law now to translate this, we can move V1 and put it into terms of current and resistance. So that's just going to be I naught times R1. V2 is going to be I naught times R2. And V3, I'm sure you've guessed already, I naught times R3. Now all we got to do is use algebra, factor out our current, and we have R1 plus R2 plus R3. So here we've satisfied Ohm's law, as long as that holds true, right? Easy peasy. Alright, how about in parallel? Well, that's a little bit harder. What we got to do is take the inverse. So the inverse of the equivalent resistance is equal to the inverse sum of parallel resistances. So what does this look like? Okay, well, let's go back to a circuit. We've got 1 resistor, 2 resistor, and 3 resistor in parallel. We've got some input current, again, I naught, and some voltage source, V0. And we know that from Kirchoff's current law, that these branch currents across each of these resistors is going to have to equal what we get in, right? So we've got I1 across R1, I2 across R2, and I3 across R3. And we know that those all have to sum to I naught. So again, what we do is we translate this using Ohm's law. So we take that current and we put it in terms of voltage resistance rather than current resistance, as we did for the series combination. So V equals IR, alright, then I equals V over R. So V naught is going to be equal, or sorry, V naught over R1 is going to be equal to I1, and so on and so forth. And we can check this too using Kirchoff's voltage law, because we know that the voltage across each of those closed paths has to be equal to V naught, since there aren't any other elements in this circuit. And again, using algebra, factor out V naught, and we get 1 over R1 plus 1 over R2 plus 1 over R3. But not quite done, as we were for the series. Because what we have here is an equivalent resistance that is equal to not the inverse, right? Not the inverse. There's no -1 up here. Well, that's because, remember, we're still in current. So if we want to put that in terms of voltage and get back to Ohm's law, we have to move it over, right? And how do we do that? Well, that's where we get our inverse from. 1 over R1 plus 1 over R2, 1 over R3, inverse. Alright, it's a little more complicated, but there's also a shortcut we can use. So let me start a new slide here and set up our circuit, and I'll show you this shortcut. So, same 3 resistors. Now, got our V0 and our I0 and each of our resistors. So let's do it the hard way first. R2, R3. So the hard way, we've got 1 over REQ is equal to 1 over, let's say, R1 is 10, R2 is 20, and R3 is 30. So 1 over 10 plus 1 over 20 plus 1 over 30. And do it on your calculator. Don't forget that this is this. So what you actually need to put in your calculator to get REQ is that. I can move that over here just to make it easier for us. But what we get is 5.54 ohms. And that's kind of tedious, right? You know, it's computationally fairly simple, straightforward, just takes a long time. What we can do to simplify this and do it in your head quite a bit faster. I know, at least for me, I have a hard time adding up fractions like that with all the conversions in the denominator. What we can do is we can say between any 2 of these elements, REQ is going to be equal, let's say R1 and R2. So R1 times R2 is equal to, over R1 plus R2 is equal to REQ between just 1 and 2. Not 1, 2, and 3, just 1 and 2. Well, let me put that there. So here we've got 10 times 20, which is 200, over 30. So 20 over 30 is the equivalent resistance. And all I've done here is, for the sake of simplicity, I'm just going to do 2 at once. So I delete these 2, and all I've done is put in an equivalent resistance between them. And this is equal to 20/3. So now, to get back to total REQ, I just do the same with R3. So I take REQ 12, 20/3 times 30, put it over 20/3 plus 30. And here on the top, we've got 200, and on the bottom, let's see, 90. Looks like 200 over 110 over 3. Let me check that on the calculator real quick. Yeah, so again, we have 600 110ths, which is going to be the exact same thing as what we got over here. 5.54. Or sorry, 5.45. Blame that on my dyslexia. Alright, so that's a simple way to combine two resistors in parallel. So let's do one more quick example here. If we have a circuit that looks like this, let's just do this one real quick. So here we've got 10, let's say 5 here and 5 there. So straight off, we know we've got 2 in series, the 5 and the 5. So we can say this branch equivalent resistance is just going to be 5 plus 5 equals 10. So we can erase that and put in our equivalent resistance. And now all we've got is 2 resistors in parallel. Okay, let's do our quick method. So we've got here 10 and 10. So 10 times 10 over 10 plus 10, we get 100 over 20 equals 5. So this demonstrates a really easy way to have resistances. On paper, we can write down whatever resistance we want, right? The only limitation is how much lead we've got in our case. But in the real world, we have manufacturers who make resistors. And you don't always have exactly the resistance you want. So if you have, say, a need for a 5 ohm resistor, but you can't find one, but you do have 10s, voila. All you have to do is find 2 of them, put them in parallel, and you have an equivalent resistor of 5 ohms. And that concludes our video for today.